We are going to discuss this another problem of the day, that is longest common subsequence. It's very famous question, and it is the question for DP, right? It is a question from DP. So we'll see why we are using DP, and also we'll go from writing the recursive code, and then we'll jump on to write the optimal DP solution for this longest common subsequence. Okay, and I hope we all are clear with what a subsequence is, and I'm assuming that you guys already know what this problem is. Okay, but let's just have a clear understanding of what this problem is asking us to do. Let's say we have these two strings, okay, and we are supposed to find out the longest common subsequence. Okay, let's say we have A, B, C, D, E, and A, C, E. Okay, these are the two strings, and we want to find the longest common subsequence. So uh, as we can see, the longest common subsequence will be A, C, and E, and over here A, C, E. So this will be the longest common subsequence. But when we had when firstly we look at this question, right? It won't strike you at first that what are we exactly supposed to do, right? But what is the magic of recursive thinking? That we assume we have a particular function that will give us the longest common subsequence for any two strings, and then we solve only one case for the current index of position that we have to solve for, right? So but there are many subsequences, right? A, B, A, C, D, A, C, E, pardon. Okay, a lot of subsequences can be there, right? Common subsequences, let's say A is common here, right? AE is another common subsequence. But what is the longest? ACE and ACE. So the length of the longest common subsequence will be 3. So I hope I'm clear on this, and let's try to code a recursive solution. So let's say I'm calling on to a helper function that is taking 2 arguments. Okay, actually 4 arguments. The first 2 will be the indexes for the strings from where we want to start. Okay, and we'll also pass on the strings. All right. Okay, what is this helper function returning? This function is returning the length of longest common subsequence for both the strings. Okay, int I, int j, string at temp1, string at temp2. All right. Okay, now what will be the base cases? Okay, let's say if I becomes greater than equal to temp1 dot size if either of the strings have terminated. Temp2 becomes greater than equal to, sorry, j becomes greater than equal to temp2 dot size. Okay, then what do? We simply return 0. Why are we writing this base case? Let's say that if we have A, B, C, and we have A, B. Let's say if J is here, okay, at B, and this is A, B, C. So and this I is at B. Okay, so if we call for I plus 1, I will become 2 and J will get exhausted. So we don't have anything to compare with string 2, right? We cannot compare anything with C. So that's why when this condition is reached, when either one of the string has completely exhausted, we simply return 0. All right, so I hope I'm clear. Now what do? Let's say if the characters at I and j are same, then what does that mean? It means that we can add 1 to our common subsequence length. Okay, so let's say we create an answer. Int answer is equal to int min. Okay, now let's say if temp1 of I equals temp2 of j, what do? We simply say answer is equal to 1 plus. Now that the two characters at I and j position are same, let me just explain. A, B, C, D, E and A, B, C. So initially I and j are 0. So we are here, right? So as we can see that these two are equal. That means we have made it to one length of the longest common subsequence. Okay, so now we will call on to the recursive function for this part, right? This and this. We'll ask recursion to find longest common subsequence for these two parts. Okay, so what do? We simply update the index by 1 and we pass on the same strings. Alright, now what if this does not happen? Okay, let me just make this as answer 1 and this as answer 1. Okay, we'll make another answer, that is answer 2, as int min. Alright, now let's say if they are not equal, then there are two possibilities, right? Either we skip j by 1 or we skip I by 1 and one of them remains at the same index. Okay, which means let's say if in place of A we had E here, okay, then A and E are not matching, so we can find longest common subsequence in these two parts. Okay, in these two parts, this and this. Okay, or else what we can do is we can increment I by 1 and we can find the longest common subsequence for these two parts. Okay, so this is what we have to do, right? Now why are we doing this? Because the first two are not equal, so we have to try out each and every possibility, right? We can either increase this and j remains at the same position, or we can increase we can increase j and I remains at the same position. So in that way we will explore all the possibilities, right? So what do we do here? We simply say that answer 2 will be maximum of helper of I plus 1 and j and I comma j plus 1 and temp 1 temp 2. Alright, okay, and what do? We simply return maximum of answer 1 answer 2. Alright, now let's try and run this code and then we will look forward to optimize it. Okay, let's see. Now as you guys can see that we are having two parameters, okay, and over here we are making recursive calls, right? So all of this code will lead to an exponential time complexity because we are exploring possibilities. Okay, so in order to optimize it, what we will do, we'll apply dp, and in order to realize that dp will be used to optimize the solution, we will have to draw a recursive tree. So I'll ask each and every one of you to draw a recursive tree for the problem that we have just solved, like for this helper function, and then you will realize that some states are repeating. Okay, let's say by any chance if I come at this b and this b, that means when I equals 2, I equals 1 and j equals 1, and if I calculate the solution for this part, if I calculate the solution for this part, then I might not need to calculate it again. Okay, so once you draw the recursive tree for this helper function, you will realize that we are actually repeating calculations for a particular subproblem, and we don't need to do that, right? Because we have this ability to store the answers, okay, in a cache or let's say a dp array. Okay, so let's optimize it. Let's say we have vector int dp, and the number of rows will be text1 dot size plus 1 vector int text2 dot size plus 1 and minus 1. Okay, we initialize it with minus 1. We pass it over here, and let me just copy this and paste it here. Okay, now one case will be if dp of I and j is not equal to minus 1, we simply return dp of I and j. All right, now let's just pass dp over here, and here as well. Okay, and let's store the answer dp of I then j. Okay, now let's run this code. Now let's try and submit this. Okay, so what will be the overall time complexity for this dp solution? Since we are visiting each and every index, at least twice, and from the parameters we can see that I and j are changing, so the complexity will be order of size of string 1 into order of size of string 2. So that will be a O of n square solution. Alright, so I hope I have clearly explained you the longest common subsequence problem. We are just assuming that we have a function that will return the LCS for a particular two strings that we provide. Okay, and on the basis of that assumption we are actually coding up our solution. So this is simple recursion, right? If you know recursion, you know dp. Okay, thanks.